Hi, this is Terry Dennery of the MathWorks. So kind of building on what we did in our last demo, is that we ran parameter estimation, we adjusted parameters like stall torque and no load speed till our simulation model matched quite well our observations from our open loop test on the voltage profile that we delivered. Okay, and at least it worked very well for these big peaks right here, right? And so we're ready to develop a control now, right? And so we're going to develop the control against the plant model of the DC motor. So we just copy all this, and I will launch a new model file, and we'll paste it in, right? And I kind of like the idea of the motor being a component at this point, and so I'm going to throw all this into a subsystem, right? With voltage coming in and angle coming out. But there's the model. And again, I'll remind us that that angle is expressed in degrees. Okay, but otherwise that looks pretty good, right? And so now let's create our controller, in which we're going to use a PID. Oops. Get the one that ships with Simulink, right? And that's going to determine the voltage that we're going to deliver, right? I'm going to double click on here because we're going to take this to hardware, and in hardware we do need to make this a discrete, that there will be a sample rate, and it's going to be the sample rate that we've been working with is 1/100th of a second. All right, and the whole idea of the PID is it will operate on the difference between what we're commanding the position to be and what we're measuring it to be. And so finding that difference is a good use of the sum block. Right. Okay. Make this real big so you can really kind of see the port labels. And then in the current configuration, it's a plus plus. But we're going to subtract off feedback, so we'll make that a minus. Let's make some more room for ourselves so we can kind of get stuff in here. And so we'll feed this back like that. And now we need to get our command signal. And so I'm going to just go to the model we used in our opening demo and just grab it right there. All right. And you'll see kind of our 4 revolutions defined and everything. So let's copy that. I think I'll copy the selector as well. And we'll paste that in. Right, and let's get a scope. Try that again. Scope, SC, there. Okay, and we'll compare what we're commanding with what we get. So just kind of going with these defaults, KP, KI, KD, default values of 1, 1, 0. Probably won't work, but let's hit the run button and find out. And that seems like that wouldn't work. That's kind of obvious, kind of unstable control, right? And now let's go in here. So that all looks pretty good. Let's, oops, not here. Go into the PID block, and we'll click on the tune button. Yeah, and I love the tune button. It's kind of tapping into all that great stuff that the MathWorks started putting into the control system toolbox probably pretty close to 35 years ago. And it's going to linearize that plant. DC motors are pretty linear systems, so in general, well, I'd say that the methodology of linear controls is very appropriate for a DC motor. Okay, and so there's calculating. And I'd say that all looks pretty good. I'm going to go ahead and kind of show you the parameterization that the tuning came up with. And so these are the values for KP, KI, KD, and they look pretty good. And so I'm going to just kind of update the model now with that. We'll see that discrete time step taking place right there, in what I'd call the staircase kind of form of the DC motor response. And so just as discrete changes in voltage, they're going to take place every, 1/100th of a second. Right. Is that updated? Yeah, it is. And so I think we can close this down. Those numbers are in there. And let's hit run again. And that looks pretty good. And so looks pretty close to what we got with our opening demonstration where we directly connected to the DC motor. And so this is a transition of 0 to 4 revolutions, and it takes place in 3 seconds. So you might recall that we identified the tougher problem, which was, let's make this happen 4 times faster. So the transition period this time will be 0.75 seconds. And I find this really interesting. And so I'm going to kind of compress this. Let's look at it from that scale. And what I think is really impressive is that it does look, again, very close to what we saw in our hardware test, where all of a sudden there's much more noticeable lag in the response, and we're definitely seeing that down here. And then there was an overshoot. And I recall our overshoot being about 80 degrees in the first demo, and we'll see that this one's about 60 degrees. And so it's not perfect, but it's awfully close. And we'll kind of work on our solution, which we introduced in that opening demo too, which is it will use our knowledge of kind of the response of the DC motor in a feed-forward algorithm and see how that addresses it. So we'll do that in our next video. Thank you.